Welcome back to Operations Research video lectures, and now we have something that's probably not very standard in typical courses in Operations Research. So we had this transportation problem, which now I call the primal transportation problem. That's very standard. That's the bread and butter of Operations Research and linear programming, really. So it's a very central problem and very important one. I think that, well, I hope it's clear to you how this can be very useful. But let's try to think about the dual transportation problem. So far we know that every LP has a dual LP, and transportation problem can be modeled as an LP. This is something that we know now already. And yes, that's actually why we called the transportation problem as a primal transportation problem in the previous section. But what is exactly a dual transportation problem? And to bit understand what is going on and how we should try to find this out is that what's the dual about? So in the dual problem, the constraints become decision variables. Decision variables become constraints. The sense, whether it's a maximization or minimization, is reversed. Okay. Now if you remember the primal transportation problem, it was a minimization. We want to minimize transportation cost. So we expect the dual transportation problem to be a natural way of maximization. Also, the constraints in the primal, they were basically twofolds. They were supplies and demands. So we expect that the dual problem has kind of two types of decision variables, those related to supplies and those related to demands. Okay, let's just denote by U the dual decision variables associated with the supplies, and V the dual decision variables associated with demands. And again, sorry for the clashing notation. So the U's will be now the decision variables in this dual. They are not the reduced costs. Okay, but you should be used to this, that different problems have different clashing notation. This is the way of life. Okay, what about the constraints in the dual? So the constraints in the dual are associated with the objective of the primal. And the primal we had, the objective is the CIJs, the root costs. So we expect to have constraints for each different I and j for the all CIJs in the dual. So this was just kind of amusing. What do we expect the dual to be somehow? So let's try to guess it. It's better to guess and then actually to prove that our guess is correct. This proof I will omit. Let's just hope that the guess is, from the guess we see that this must be the case. So what happens? So we start that this is the normal formulation of the primal transportation problem. I think it's good to see this again, just to see what it looks like. So we have to minimize the total transportation costs such that the supply constraints are true for all the sources, demand constraints are true for all the destinations, and yes, we have the sign constraints. And in some sense it looks at to put this in the standard form, standard primal form, is not a good idea because it's a minimization. So let's transform this as a standard dual form, and then we know that the associated standard primal form is the dual of the dual. So we keep the minimization as it is, and the only problem here is that these are upper bounds, so let's put them lower bounds. And this is done simply by multiplying by -1. So now this is actually a dual standard form. It doesn't look too much that because we have these xij's and not just vectors, so we have matrix notation there. But I hope that it's kind of somehow with the correct unfolding, if you like. This is the dual standard form. Okay, so the dual of this dual standard form, again I repeat, the dual of a dual is primal. We go the other way around, so minimization goes to maximization, these here go to the objective function, and lower bounds become upper bounds, and here we have these Cij's come from here, and what else? So somehow these minuses go to the constraints, and it actually, if you think about it, just believe me, this is what happens. So the dual is a maximization. Now I put the W just to the duality z and W. Usually we had a minimization W, maximization z. Let's have it this way, doesn't matter really. So we have to maximize minus sum of ui's si's plus the sum of vi's dj's. So this is how the objective comes from, this minus si's and dj's. This minus here corresponds to this minus here. And then the vi's minus uj's must be less than or equal to cij for all I and j. Okay. And again, this minus corresponds to this, and then this double sum. Because there is a I times j actually variables here. So we have I and j, I times j constraints here. And the standard thing that these are non-negative. So this is formally what the dual transportation problem looks like. And what does this mean? Can we interpret this? And yes, we actually can. I mean, it could have been that we know that there is formally a dual, but it could be that the dual problem is an obscure problem. It's kind of impossible to interpret in a natural way, but here we can do it, at least a relatively natural way. And this is the problem 9.9. Spice must flow with no ships. So let's have a story here. The Ixians have invented the so-called no ships that do not need spacing guild navigators. So they can compete in providing interstellar travel. And now what the Ixians do, they want to make an offer to the case to take care of the spice flow problem 9.1, which we had. And how do they do it? They offer to buy the spice from the sources with unit price ui. So ui is the price per unit of spice they are going to offer to buy from the source I. And then they offer to transport it somehow to the destination j, and there they will sell it with the price vj. Okay. Now the question is, what should the actual offer, these ui's and vj's, so unit prices for buying and unit prices for selling in different sources and destinations, what they should be, so that these sources and destinations say that, okay, we are not using the spacing guild for our transportation needs, we just sell and buy our spices, and the Ixians take care of these transportations any way they like, and that's it. So that's an interpretation of this dual problem in this case. And maybe this 9.10 remark, highliner, no ship duality is in order. So this has to be understood. One way to understand the duality, of course, this is just an imaginary story. But what's important here that in some sense the spacing guild transportation schedule, so costs of transportation, they are public information. Everybody knows what it is, and the sources and destinations, they have already agreed that the spice from here goes there, but they then have to pay for the transportation for the spacing guild. But now these mysterious Ixians come, so the sources and destinations, they don't really care how the transportation is handled, and the Ixians are not going to tell. Maybe it's a secret, and yes, that's the kind of mindset what happens there. All right, here this is more or less what I said. So the problem 9.9 is really the dual of 9.1, and maybe I repeat the story here just to make it clear. So the Ixians want to take over the business of transporting spice. So if they offer UI per unit from source I, and then to buy, and then Vj is the offer per unit to sell for the destination J, then the total revenue the Ixians get with this buying and selling is, of course, this. So U is buying, so this minus U is what they get, and they are all the supplies because they handle the whole business, the whole transportation. So this is similar to the duality we had with the product mix problem and the nutrient problem. You buy everything. And so this is what they will pay in the source side, and this is what they get back in the destination side. Okay, so that's the minus sign here. So what about these constraints? So now each pair, source I, destination J, remember they already have the agreement that things will be transported. Now they think that, okay, whether we use the Ixian no ships or the spacing guild highliners. And if the Ixian offer is such that this difference, so this is what the Ixian sell, things that they have bought here, if this costs less than the transportation, it makes sense for these planets to move the spice by using Ixian no ships, than the spacing guild highliners. So consequently, the Ixians can take over the transportation business. Okay, so then there is this problem. Now it's formulated. So it's really formulated here, 9.8, and then they solve it with GLPK. And yeah, again, is this easy to formulate for GLPK? This part is probably not too difficult, but this Vj minus Ui is less than equal to Cij for all I and j. So there is, for each I and each j, there is a one constraint. So there are actually lots of constraints. So this is the kind of pain in the forehead to do. And let's do it in a quick and dirty way, just to see what this kind of formulation, where these kind of for all this and that, they are easy to write mathematically or semi-formally like this, but then to actually implement them in a computer is sometimes a bit tedious. So let's see how this tedious thing goes. So here is the 9.11 solution, spice must flow with no ships, quick and dirty. Again, as always, here is the link for it, so you can download it, and you should download it, and then move to your Octave working directory and run it there and see that it works. So how does this quick and dirty goes? Let me explain this a little bit, and I think it becomes very clear that this is indeed quick and dirty. So S, D, and C. So this is actually the original data of the primal transportation problem. But this is the data for the dual also. So how is it? So we have supplies, we have demands, and we have the cost matrix. So the first thing to transform these into the LP formulation, we need of course the C, A, and B. So what is the C? C is in this dual formulation. Yes, this is now in standard form. Dual is in primal standard form. So the C is they are minus S's first, and then plus D's. And this is just a sum, but this is how it goes. So this is easy. C is minus S followed by D. Let's then consider the A. This is the kind of tedious thing to do. Very easy to do a mistake here, but let's hope that this is now correct. So what's the A here? A will be the constraints here, Vj minus Ui for all I and j. So I have to have plus 1 for Vj and minus 1 for Ui for all the possible pairs of I and j. And this is what happens here. So this is the matrix. There are 6 of them because there are 6 constraints. Remember, there were 6 decision variables, the primal, so you expect that there are 6 constraints in the dual. And they are like this, and I have written here in the comments what happens there. So for example, the first one is V1, that's this, minus U1, that's this. And the other variables don't show up here. Then there is V2 minus U1, V2 is here, minus U1. Then there is V3 minus U1, V3 is here, minus U1. And the same for U2s. So if you want to make not quick and dirty but an elegant, you can probably see here that maybe there are these identity matrices here going down now, not going that way as in the primal. In the dual they go down, obviously. And then, okay, then there are these ones flowing down like this, but they are actually minus ones because it's a minuses here. So here the variable U1, U2, V1, V2, V3, and like this. So probably if you understood how the transsolver worked in the primal case, how this A was in the primal case built, then maybe from here you can see this is a similar thing happening in the dual case. Of course, this is what you expect. And this A is somehow the transpose, or actually minus transpose of the original one. Well, not quite, because there are minus signs here, but not here. Okay, so that was a technology. So technology was the coefficients here. Then we need the upper bounds, Cij. So we have to unfold this. And we could use this C prime and then the colon unfolding, something like that. I do it by hand here, just to make this very quick and very dirty and very clear what goes on. So this is dirty, but it's clear. So this here corresponds to C11, this corresponds to C12, this C13, note this go the other way around, 1, 3 and so on. So I made quite many mistakes before I got this correctly. So the B's will be the matrix A unfolded this way. So I did this very quickly, very dirty by hand like this. Okay. Then we can solve it with GLPK. So let's see how this goes. So I solve it by, okay, I use now the solution will be UV. I just named it like this, for the reason that is soon obvious. So that's the optimal decision. So these are the optimal prices per unit per megaton of spice offered to buy and sell, depending whether it's a source or destination. So GLPK, so this is standard form, so this is what we have always: C, A, and B, empty, empty, use for all the bounds, C is for all the variables, and it's a -1 maximization. So these are just, we have, I think these are clear. So then a little bit, so U, this will be the first three decision variables, sorry, two, U1 and U2, and then we have three. So these are the source side, these are the destination side. So indexes from 1 to 2 from this U, well, they have all U and then V are here, and then the last one from 3 to 5 indexes will be the V, and then there is here's the cost. So the missing semicolons here mean, as always, that here the solution is printed out. So in this section we solve with GLPK, we split the solution. So here is solving GLPK, here is splitting the solution, and finally printing out. The printing out means the missing semicolons here. And again, as always, let us copy in this file, or in this file is copied the test result. So no-zip quick and dirty will give U is 2 and 0, V is 565, and the cost is 153. Okay, so what does this solution mean? Okay, this is actually quite an interesting thing. So these are the buying price. So what is the Ixian offer? So in Arrakis, they will offer to buy all their spice with 2 billion solaris per megaton. Okay, why not? This 0 is a rather curious thing. I'm not completely sure what to make of it. It says that the Tleilax, they go and say, okay, we will transport your stuff, but we pay nothing. You just give us your spice and we transport it. Okay, this is very curious thing. And then in the Caladan, they will sell the spice with 5 billion solaris per megaton. That's this. In Kaitain, they sell it with 6 billion per megaton. And finally in GD Prime, they sell it with 5 billion solaris per megaton. And with these prices, what is the profit? So the business of the Ixians were buying these spice and selling them and using the money to make the transport however they can make it. And this will cost the Ixians something how they do it, but the revenue they get out of it, this transportation, taking care of this transportation, is 153 billion solaris. And this is, of course, this is the optimal shopping cost for the Spacing Guild. And I mean, this is certainly no coincidence. They should be the same. They are in duality. Okay. So that was the dual transportation problem. And finally, exercises for the dual transportation problem. And yes, exercise 9.12, spice must flow with no zips. So it is the basic problem we had in this section. And the solution 9.11, which we just saw it was here, this stuff. Yeah, it was quick and dirty. And why is it quick and dirty? Well, it only works with the very special case of the question. Now we have this transsolver that worked for every transportation problem, basically. Now it's obvious question is, can we do a similar thing for these dual transportation problems? And this is indeed what what is this exercise about. So you have to make GNU Octave function dual transsolver. That should work exactly as a transsolver, but it solves the dual transportation problems. And then you should to check that your function works, solve this problem 9.9 by using dual transsolver. Okay, what about this problem? Is this difficult or is this easy? And if you start from scratch to do this dual transsolver, if you do that, then of course you should look at the transsolver and take some hints there. Building a technology matrix A will be relatively complicated. As it was in a transsolver, it will be in the dual transsolver. To build this in a general form, it is I expect you to do a lot of mistakes when you try to do it, and it will take some time to get it right. So it is not too easy. But there is now, since we have a lot of stuff here, there is actually a easy way of doing it. The easiest way to do it is actually, if you look at the transsolver, it solved the primal problem by using GLPK. Well, the GLPK will of course solve the dual problem also. You can just ask the extra parameter there. And now you can actually make or extend the transsolver so that it will both solve the primal and the dual. And this shouldn't be too difficult. Okay, you have to split probably the shadow prices to the UVs. So remember that shadow prices of the primal transsolver lambdas will correspond to dual variables that are the U's and V's. And the total cost will be the same, of course. So that's a programming exercise that can be very tedious, but it can be very easy if you understand what this duality is all about. And then a final exercise in this chapter 9, 9.13, exercise more spice. So this has to do again with the unbalanced situation, but now we're looking at it slightly different than before. So there was more spice found in Arrakis. So there are now 23 megatons there, and now we have excess supply, but we want to keep the things balanced. So this excess supply of, it was 50, now it's 23. I hope that 23 minus 15 is 8. So there is excess of 8 megatons of spice, and this excess supply was promised to the planet Chapter House. So then the transportation costs from Arrakis and Tleilax were negotiated with the Spacing Guild, and the result is stated in this following table. So this is the same table that we had this highliner spice transportation as before, except what is here in the boldface. So there's a Chapter House has this 8 megaton of demand, and Arrakis has this 3 megaton supply. So 23 plus 20, which is 43. I hope that it's the same number as here. And then these are the costs that were negotiated with the Spacing Guild. So from Arrakis to Chapter House is 3 billion Solaris per megaton, and from Tleilax to Chapter House it will be 5 billion per megaton. And now, the question. First, solve the optimal transportation schedule for the Spacing Guild. So this is just to solve this variant of the problem 9.1 that we had. And also solve this problem for the Ixians. So what would be the Ixians counter offer here to taking care of this whole business so that spacing Guild are out of the business. So that's the problem 949 for reference here. Okay, that was chapter 9, and in the next chapter we will actually continue with transportation problems. See you in next video lectures. Bye.